All right, this is going to be the lecture video for Chapter 2, One-Dimensional Kinematics. So one-dimensional kinematics means for this chapter, at least, we are only going to worry about objects going in one direction. Object is either going to go horizontal or it is going to go vertical. Those are the only options. Sometimes for students it's easier to see this using some sort of number line. So in this case, this example, they have a particle and it moves in the positive x direction. So it's going horizontally. If you think of a graph, x is your horizontal axis. So it goes in the positive direction for 2 seconds and then it reverses its direction. So you can see it starts out at time 0 and it started at 1 meter and it went for 2 seconds in the positive x direction and then it came back for the other 2 to 5 seconds probably. But sometimes seeing a number line helps visualize the one dimension. So big topics for chapter 2 are the difference between position, distance, and displacement, the difference between average speed and velocity, talk about instantaneous velocity, acceleration, what happens to your motion when you have constant acceleration, applications of your equations of motion, aka your kinematic formulas, and talk about when objects are freely falling. So before you even want to describe your motion, you want to make sure you have a coordinate system that makes sense to you. The easiest way to do this is by doing a number line, or especially when we get into two-dimensional motion, think of it like a basic graph. That's the easiest way I explain to my students. Right? Make your horizontal x, go to the right being positive, left is negative. If you're talking about vertical, going up is positive and going down is negative. Easiest way to think about that. For the example shown here, right, you have x, so the guy is going horizontally, and he's going in the positive direction because he is going to the right. You have his initial position, which is not at origin, right? Origin just means 0. Where's your 0 value? His initial position, so you have x of I, and then his final position, x of f. So this is just a basic coordinate system to help you figure out which way is positive and negative. Distance is the total length of travel, regardless of direction. If you go from your house to the grocery store and back, right, between your house and the grocery store is that 4.3 miles. So if you go there and you come back, your total distance is 8.6 miles. Distance is a scalar quantity. It does not rely on direction. It could quite literally care less about direction. It just cares about the total amount that you moved, whether you go forward and backwards, up and down, right, left, or you can go right, right. It's just the sum of the total length of your travel. Displacement, on the other hand, is the change in position. It measures from where you start to where you end, and nothing in between. So if you drive from your house, right, so your house is right here in the center, you drive from your house to the grocery store. That's the first step. So you go 4.3 miles. I'm going to say this is to the right, so that would be positive. And then you drive to your friend's house. So you go from the grocery store all the way to your friend's house. So you went 4.3 miles from the grocery store to your house plus the 2.1 miles. So 4.3 plus 2.1 gives you 6.4 miles, but in the negative direction because you were going to the left. So while your total distance you traveled is 10.7 miles, you add the two together regardless of the signs and the direction. When you calculate displacement, you can either take the difference of these two because you're going in different directions, or you can measure from start to end, which would be from your house to your friend's house, which is 2.1 miles to the left, and negative because it's going to the left. That is a negative. So displacement is negative 2.1 miles because you only care about where you started, which was your house, and then where you ended. Does not care about the grocery store in between. Distance cares about you going to the grocery store and back. So distance is the total that you travel. Displacement only cares about from start to the end. That's it. Okay, so that was all position, distance, and displacement. Figuring out where you are. Then we have to talk about the next step up, average speed and average velocity. So average speed is the total distance you travel. So whether you go forward and backwards, left and right, take all of that into account, and the total amount of time. So total distance divided by the total amount of time. Average velocity is your displacement divided by the time. So going back to those scalar and vector quantities. Scalar quantities don't care about a direction. Speed doesn't care about a direction. So what I tell my students is that speed is a scalar value. S and S, they go together. So if you want to find speed, then you do distance divided by time because distance is also scalar. Velocity is a vector quantity, right? Velocity cares about direction. Displacement is a vector quantity. Displacement cares about direction. So V and V go together. So average velocity is displacement over time. And then this one always gets students confused. If you start and end in the same place, you started at your house, you ran to your friend's house, and you ran back. If you started and ended in the same place, your displacement is 0. Therefore, your average velocity is 0 because you have no change in displacement. Remember, displacement cares about where you start and where you end. So if you started and ended in the same place, it's kind of like you didn't move. Would you calculate your average speed, then you would take into account the total distance you went between you and your friend's house and the total time that it took. All right, this is a more visual representation of your average speed and velocity. This is putting it onto a graph. So in this class, you're going to see 3 common types of graphs for kinematics. You will have a position versus time graph, aka known as a X versus T graph. Time is always on the x-axis, position, displacement, and distance all are considered the x variable. It's all the same thing. They all measure some sort of length. And that is always on the y-axis. So you can see on this graph right here to the right that your object started at 1 meter. Then as time went on, it traveled a total of 3 meters in the first 2 seconds. Right? So you go from 1 meter to 4 meters, it traveled 3 meters total. This section has a positive slope. That means you are going in the positive direction. Then, when your object is at that 4 meter mark, then you see a negative slope. This means that you are changing direction, right? You are going backwards. You are going back to your starting point, right? Your starting point, right, was at 1 meter. So in between 3 and 4 seconds, you were back at that 1 meter, but you really ended to the left or backwards from that in the negative direction. All right, this graph represents that first picture that we saw at the beginning of this lecture. At time 0, you start at 1 meter. After a second, you were at 3 meters. It's just putting it on a graph for you. That's all this is doing. Instantaneous velocity is defined as the change in x over the change in time. Change in x is the change in displacement. So you typically evaluate average velocity for shorter and shorter period of time as your problem goes on, until that time becomes so small that you have instantaneous velocity. In other words, instantaneous velocity means the velocity right at that point in time. So if you want to figure out after 3 seconds how fast you were going, you can do that. But that's only at 3 seconds. Doesn't take into account the entire trip. Instantaneous is only at 1 point in time. That's it. So this is another graph, right? Another position versus time graph. Blue line is your motion, right? Start at 0. And after 3 seconds, somewhere between 25 and 30 meters, right? So probably like 27 meters. So you can measure the average velocity between different periods of time, right? You start out at a longer interval of time, right? So that's this value, right? And we get the average velocity to be 13.7 seconds. Do it for a shorter amount of time, 12.1, right? Because you're going from here, here, so much until you get tangent to that curve to get your instantaneous velocity. Another way to show both average and instantaneous velocity. So if you take the slope between 2 times, whatever 2 times that are defined, you'll get your average velocity. Right? If you take the slope of the tangent line right up against the curve or the line, then you get instantaneous velocity. Okay, so moving up in the world, we've gone from distance, displacement, position, right? Figuring out where you were. We talked about speed and velocity, how fast you were going and in what direction. Now we talk about acceleration, that change in velocity over time. So for average acceleration, this tells you how fast were you changing your speed. Take your final velocity, subtract it from your initial velocity. Your change in time is your final time minus your initial time. most of the time for t, most problems, you start out at time 0. Right? Unless for some reason you started time 1, like in our graphs before, 95% of the time you will start out at time 0. So then you would just use your total time they give you in problems. Velocities work kind of the same way. Sometimes your initial velocity, what you start out with, is 0. Sometimes they'll give you an initial velocity. Kind of just depends. But this table shows you different accelerations from different scenarios. So if you hit a baseball with a bat, your acceleration of that baseball is about 3 times 10 to the 4th meters per second squared. The acceleration of gravity on Earth, which is going to be very useful to know, is 9.81 meters per second squared. This is going to be used in free fall and your kinematic formulas for free falling objects. All right, more graphing for acceleration. Again, if you take the slope of the tangent line of a velocity graph this time, notice this one is velocity, the slope of the tangent line for velocity gives you the instantaneous acceleration, while the slope between two different times gives you the average acceleration. So one thing that helps my students is that the slope of a position, distance, whatever graph versus time, if you take the slope of the line, you are getting the velocity. If you take the slope of a velocity versus time graph, which is what this one is on the screen, you will get the acceleration, right? Velocity is measured in meters per second. Position versus time is meters versus seconds. So meters per second. Velocity versus time graph. Velocity is meters per second versus second. So sometimes you'll see acceleration as meters per second squared or meters per second per second. Both are valid forms for units for acceleration. All right, so acceleration and deceleration should not be confused with the directions of velocity and acceleration. This one always trips up students, and it is so much easier to do if you have pictures or draw pictures. All right, if you are accelerating, you are increasing your speed. If you are decelerating, you are decreasing your speed. All right, notice though, it's talking about speed. Speed doesn't care about direction, remember? So you can be accelerating in the negative direction and decelerating in the positive direction. It sounds kind of weird. But for example, in picture A, you have the car. The car is going to the right. He has a positive velocity and he is speeding up, so acceleration is positive. All right, to the right means positive, not always the numbers getting bigger. Not always. In picture B, the car has a velocity going to the right, but the acceleration is negative. You are slowing down. In picture C, car is going to the left, the speed is decreasing. So that means your acceleration is to the right. And then picture D, your velocity is to the left, and your acceleration is also to the left, means your speed is increasing. Another way to think about this is speed is increasing when both velocity and acceleration are in the same direction. Speed is decreasing when they are opposites of each other, when they are going opposite directions. All right, if you have constant acceleration, which 90% of this class it is going to be constant, then your velocity is going to change linearly. It's going to change at the same rate over the same amount of time. And you get your first kinematic equation, which is your velocity, your final velocity. Right, this should really be final. That's an F. Is equal to your initial velocity. Sometimes you may see this as V with a small subscript of 0, or you might see it as VI. Both are acceptable. Plus the acceleration times the amount of time that it takes. For average velocity, right, you would take both your starting and your final velocity, add them together, divide it by 2. It's an average. 2 values, add them together, divide by 2 is another way to do that. All right, here are more of your kinematic formulas. All right, there are a total of 5. We just saw one of them on the previous slide. Actually, technically 2, because this one was also on here. Average velocity is part of that too. Then you have your position equations, right? Position is x, distance, displacement, position, all represented by x. And then velocity is a function of position. So velocity, but you have acceleration and position. There is no time. So if your problem does not tell you time, you could use this formula. All right, if you have an object that has constant acceleration, that means on a position graph, your line is going to be curved. If lines are curved on position graphs, you have acceleration happening. Your velocity is changing linearly, but your position is having an exponential effect, right? If you have a positive exponential curve, you are accelerating. You are speeding up in the positive direction. If you have a negative slope for your curve, then that typically means you're just going the other way, accelerating. Here are all of your kinematic equations based on the fact you have constant acceleration. But these are your 5 standard kinematic formulas that you will be practicing with and need to know. Notice though, in these 5 equations, they have some of the same variables, right? Initial velocity, velocity, position, time. Each equation is just missing one of those variables. So if your problem doesn't tell you, for example, a position, right? It doesn't tell you x, then you would probably need to use one of these 2 formulas, right? These don't have x in it. If you don't have x, you can't use those formulas. That's going back to the guess method, right? Writing down what you know, what you're looking for. If when you do that, you don't have position, then you can't use an equation that has position in it. All right, so then we talk about some applications, right? Most commonly with with one-dimensional kinematics, cars, skateboards are usually the common examples, right? So if you were hitting the brakes, right? You're driving, something goes out in front of you, or someone slams on their brakes, you might want to hit the brakes too. So comparing velocity and position on a graph, right? Your initial velocity, if you were going, and then you need to stop, obviously your velocity is going to get smaller. You are going to slow down, hopefully, and not hit the person in front of you. But your position gets bigger, right? You are traveling more. You are going a longer distance. So when you hit the brakes, all right, starting out with a high velocity, then getting to lower velocity, and then increasing your position, right? This is decelerating, right? You're slowing down, hopefully. But the stopping distance, relies on the velocity that you're going. If you are going really, really fast, you're going to need a lot more time and distance to slow down, unless you're going to hard brake and ruin your car in the process. All right, last topic, freely falling objects. Free fall is the motion of an object that is only subject to gravity. I'll say it again, only subject to gravity. Gravity is the only thing that is affecting it. There are no brakes, there are no gas pedals, nothing. It is just falling. The acceleration due to gravity is that 9.81 meters per second squared I talked about earlier. It is represented by g, lowercase g. All right, if you are doing problems with kinematic formulas and your object is falling, that acceleration in your equation, right, so like 1/2 at squared, that a is the 9.81 meters per second squared. All right, you don't have to calculate acceleration for freely falling objects. Acceleration is a given value. Okay, and then just fun facts, right? Because based on where you are on the Earth, your gravity, your acceleration and gravity is just a tiny bit off from each other. So like at the North Pole, your gravity is the highest. If you go to Ecuador, right towards the equator, your gravity is lower. So as an average, acceleration due to gravity is 9.81 meters per second squared. But just fun little facts to see what gravity is at different locations on Earth. Okay, now in physics, I like to use the phrase that we are all in the perfect world. Everything in physics makes sense. There is no air resistance happening, but in reality there is. Okay, in your problems that you do, assume the perfect world. All right, we know, right, just based on our observations, that if you have an object falling through the air, you have air resistance happening. Okay, so technically it is not really freely falling. But for our practice problems and stuff, we assume no air resistance most of the time, just to make the math easier. That way we don't have to do air drag and calculus and stuff like that. All right, so from the perfect world, when you freely fall from rest, so think of dropping a ball from the top of a building, after the first second, your change in velocity is 9.81 meters per second. Okay, 0 to 9.81. That's the same as your acceleration. Acceleration is the change in velocity. Right? Then after the second, your object is now at 19.6 meters per second. Then 29.4 and 39.2. So you are increasing your velocity at a constant rate, right? Constant acceleration, constant change in velocity. Your distance, though, your position, is that exponential, right? It's not increasing at a constant rate. It's not increasing by 4.91 every second, as evidenced here, 4.91 to 19.6 meters. That is different than from 19.6 to 44.1 meters, right? Your x is that exponential curve. Velocity is increasing linearly. A more graphical representation, and this one does a really good job, of showing you the position versus time for a freely falling object, or known as a projectile. All right, a projectile is anything that is thrown, launched, fallen, and is subject to gravity. That is more in 2D kinematics in the next chapter, but same thing here. So if you start at position 0, so if you are assuming, right, that you are standing on the ground and you throw a ball up in the air, right, the ground is point 0. You throw that ball up and up and up and up, all the way to 40 meters. When it hits that 40 meter mark, or right above 40 meters in this graph, then the ball kind of stops for a second, and then it comes back down. Right? So your velocity is getting smaller as you throw your object up in the air. Right? And we've all done that. We've all seen that. When it hits its max, the velocity is 0, then it comes back down. And as it comes back down, it is increasing in speed, but in the negative direction because it's coming down. I also want to make a note that even though we're not doing 2 dimensions yet, this is really important to know. These velocities that are on this picture, these are vertical velocities. These only apply in the vertical direction. Horizontally is a whole different case for velocity. But we'll talk about that more in the next lecture.